Welcome to the third exercise for the lecture Adaptive Filters. In this video, we'll cover the iterative adaptation algorithms. This video consists of 4 sections. In the first section, I will review the iterative algorithm basics, and I won't cover the individual algorithms there in too much detail, because in the second section, I will give you a guideline on how you yourself can characterize the individual algorithms yourself. And then in the third section, we will have a comprehension question section, and the last section is again a Python demo. So let's get started. We will go through the basics by looking at the system identification problem. And in this problem, we start with an impulse response H, and this is an unknown impulse response, meaning that it is either an impulse response that we just don't know the coefficients of, or it's actually a system that we want to approximate using an impulse response. And we represent either one by our impulse response H, and this is our unknown impulse response. And then of course, when we say we want to estimate that system or that impulse response, we introduce H hat, which is the estimate of H, of course. But here I introduce a time dependency with N, because we will be using iterative algorithms, meaning that we will change our estimate in every time step. And then the only way to learn something about our unknown system is to excite it. And we do this with an input signal x of n. And of course, we can then observe the output signal. This here is d of n. And we can also just call it our observed output, because this is something that we then can work with. And when we then introduce a parallel path to this, and we say that, okay, we have our estimate, it's initialized in some way maybe, and we excite it with the same input signal, then the output of that will be d hat of n, and d hat of n is then an estimate of d of n. And then if we do it like we did in all the other lectures before, we look at the different signals between the observed output and the estimate of that output. We have our error signal. This is E of n. And this error signal, together of course with our excitation signal, we can then use in our iterative algorithms to change our coefficients in our estimated filter in every time step. And this is denoted here by feeding back our error through this H hat block here by our error, meaning that this we can use to change and improve our coefficients and our estimate. Okay, so this is then our block diagram, but what is the iterative principle? The iterative principle is that we change our estimate in every time step, and the new estimate always equals to the old estimate. So we are reusing what we have computed before, and we are reusing it in such a way that new estimate is always the old estimate plus a correction term. And if we want to put this into a formula, this is then that our H hat in the next time step at n plus 1 equals to H hat at the previous time step or the current time step, so at n. And we add a correction term. This I denote here by delta. In our iterative principle, we also have something that we call a step size. We can add this before here. And the step size actually represents in some way how much we trust the correction term we just computed. And this becomes important later in the lecture when we look at control, because actually up here in our block diagram, when we observe our output of the unknown system, we can also have noise. A lot of times it will be measurement noise, but this can also be other additive signals. And then we might not trust the correction term that we compute as much. It's erroneous in some way, so we can apply a step size there to account for some of that. But actually, how we will choose the step size adaptively, we'll see in a later lecture. And this update equation that I just wrote down for you, you should always remember, as all the update equations we will have for all the adaptive algorithms will look somewhat like this. So this is the basic recipe here. But this correction term, how do we actually compute that? We can generally say it's made up of two functions, one function g that depends on the input signal of all samples of that, and a function f that takes information from our error signal. And the way that I wrote it down here is maybe not correct for every case, because we might take all samples of E as well, or we might do some recomputation, but in general, we will be using some version of our input signal and of our error signal to compute the correction term. And what this correction term looks like specifically, this then depends on the cost function that we set. And in the lecture, we had three different cost functions. We had a cost function for the least mean square, or the normalized least mean square. This was the expectation of our squared error signal. Then the affine projection algorithm, that one had a cost function that was a little bit different. This one didn't look at one sample of the error signal, but it was looking at an error vector that we want to minimize. And of course, when we're looking at vectors, we will not just have to look at the squared signal, but we have to look at a norm of that vector. And then the RLS algorithm, that one looks at a temporally weighted sum of all our error samples that we have. And here I'm denoting something that is maybe new. I'm saying that we have a error signal L independence of n. And this basically means that I'm computing my error signal like I'm used to up here, but I always use the estimate of time step n for this error signal. And these three are then the cost functions, and from these cost functions, the individual correction terms for our iterative solution are then derived. And this is the principle of the iterative algorithms, and in the next step, you will learn a bit more about what the actual algorithms, depending on those cost functions, look like. For this purpose, I am providing you with a table that you can treat as a guideline or a template to characterize any new adaptive algorithm. And you can also apply this template to the algorithms that we've treated before, like linear prediction and the Wiener filter, for example. So let me walk you through the different bullets that I have here in this template. Whenever you learn about a new algorithm, you first need to look at the block diagram to know in what context the algorithm is used. And this is what I also did whenever I introduced a new topic to you. I drew the block diagram. So this is the first thing you do here. And in this block diagram, we always use signals. So you should always write down the definition of those signals. This is what I usually did in my right column in my introduction sections. And then most algorithms, in their derivation, they make some assumptions about signal properties. With some algorithms, they don't have any assumptions about the signal properties, but some algorithms, for example, the LMS algorithm, there we made assumptions regarding our signal properties. So this you should always write down here what assumptions were made in the derivation of the algorithm, because this influences the performance of the algorithm regarding different signals. And then the next vital information regarding an algorithm is the cost function or the error criterion that was used to derive the update equation. And I wrote you down some of the cost functions in the introduction section. And with this cost function and the assumptions, we get our update equation, and this you write down in the next step. And with this update equation, you can directly apply the algorithm. But we have different algorithms that we can use, so you always need to make a selection which ones to use. So we need to look at algorithm properties. And one property is complexity. So how many mathematical operations do we have to compute to make one algorithm update? And when we say that one multiplication and one addition, we count this as one mathematical operation, then we need to see how many operations do we need to perform depending on the filter size n or some other algorithmic parameter. How many operations do we have to perform for one algorithmic update? And then when we have these different numbers, we can see which one is the cheapest, and if there are some other which are more expensive. And then in the next section, we will look at which properties might actually lead us to accepting the application of a complexity-wise more expensive algorithm. And by properties here in the last section, I mean something like conversion speed, for which input signals the algorithm works well. You could also denote there something about the step size. So anything that influences the algorithm behavior or the performance, or there is some observance about the performance. So in the last two sections, you actually get information about when to apply this algorithm. And with this entire template, you get the information on in what context to use this algorithm, how it was derived, with what assumptions, what the equation is that you actually need to apply this algorithm, and what properties the algorithm has to maybe select the algorithm for your own application, or maybe to go with a different algorithm. So my suggestion is that for every algorithm retreat here, you print out one of these tables. And when you go through this exercise and through the lecture and maybe some other material, you fill out this table. And when you've gone through all the material, you have characterized all the algorithms and you know everything about them. Now we move on to the comprehension questions. In the course material, you actually have quite a lot of questions this time. And here I will only cover 2 questions, and those are questions that are useful to cover for the Python demo, which is up in the next section. So let's get started with the 2 questions that I have selected. The first question is, what are the 2 error measures discussed in the lecture? And why may a normalization be useful? And what are the advantages and disadvantages of the error measures? Okay, we had 2 error measures in the lecture. One was the mean square error, and the other one was the system distance. And the mean square error, like the name says, is the expectation of the squared error signal. Here we are working with the absolute value because we don't have any assumptions about our signals and they may be complex valued. And with the system distance, we don't look at the error specifically, but we look at how well we achieve the original task of estimating the unknown impulse response. So we look at the difference between the true impulse response and our estimate. And because we are looking at vectors, we are looking at the squared norm of that. And this is then the system distance. Now, if we want to look at advantages and disadvantages, both measures give us information about the general performance. The system distance gives us good information about how close we are to the system. So if this is our actual task, then this is the preferred measure. But here you see in this equation that we actually need the coefficients of the unknown impulse response. And of course, this is the entity to be estimated. So in most cases, we cannot actually compute the system distance. And this is then where the mean square error usually comes in. This is a measure that can always be computed. And sometimes actually the error is something that we want to minimize in the application as well, for example, in echo cancellation. So this gives us also some more information for certain applications. But the problem with the mean square error is that the error is very signal dependent on our input signal. So having a low mean square error value does not necessarily mean that our system distance will be low, because you might not have estimated all frequencies well of our impulse response, because those frequencies were not present in our input signal. Then for that input signal, the error is small, but the system distance will be large. So if we want to have a measure that gives us universal information for all input signals that are to come, then the system distance is the measure of choice. But of course, the measures are related, and as you saw on the lecture, when you have the input signal, you can actually compute the expectation of the error from the system distance. Okay, so where does the normalization come in? When I normalize, I can, for example, normalize the mean square error to the power of the input signal, and I can normalize the system distance, for example, to the norm of our unknown impulse response. And by doing this, I make things comparable between different system setups. So setups where I use a different input signal, or where I have a different impulse response that I want to estimate, and to then compare performance of algorithms between those different setups, I need a common reference point. Or here I mean with common reference point also that I take some variables that don't necessarily concern the algorithm itself out of the equation. And here this is the input power and also the power sort of the original impulse response. Now I want to introduce you to two other measures that you will actually find quite often when we look at echo cancellation tasks. And the one measure is echo return loss, and the other measure is echo return loss enhancement. And actually echo return loss, this is actually the same as the mean square error, but it's a flipped version of that. And then echo return loss enhancement, here we don't reference the power of the input, but the power of the observed output. So in terms of echo cancellation, this is actually when I observe an echo, I hear an echo, this is by how much I then reduce the echo by, for example, how many dB. And by taking this reference point, I actually take both the input signal and the impulse response sort of out of the equation when analyzing the system performance. So the two measures that were the ones that we had in the lecture, and the lower ones are two that you will find quite often in applications. And just so that you are aware of that, with the upper measures, the optimal point is low values, but with the lower measures, actually higher values mean a better performance. The second question is, what is the geometrical explanation for the LMS and LMS adaptation behavior? So for this, we need to look at the update equation. And the update equation for the LMS algorithm is that our new estimate, so h hat at n+1, equals to h hat at n plus our step size mu times our error sample e of n times our excitation vector x of n. And our excitation vector consists of the samples from x of n to x of n minus capital N plus 1, where n is our filter length. And then the update equation, which is an iterative one, we can rewrite it. We can rewrite it as a sum. First of all, we can pull the step size out of the sum, and then we have a sum from 0 to small n, and it's a sum over our error samples times our excitation vectors. So we see that the estimate of an impulse response at n+1 equals to the sum of all past excitation vectors weighted by the individual error samples at the current time instances times the step size. And when we want to interpret that equation, we can say that h is estimated by a linear combination of past input vectors. So for a good performance, we can say that up to time instance n, all the past input vectors x of I, they need to span an n-dimensional vector space. And since an n-dimensional vector space has n bases, we need at least capital N iterations for a good performance. And to be more specific, what is our desired property for our excitation vectors? When we look at the inner product between two excitation vectors at times I and j, then we can say that the inner product equals to alpha ij for all ij smaller than the filter length, and if I and j are not equal. And the inner product just equals to alpha I if I and j are identical. We can just say that alpha is some real number. And the desired property here is, if we had actually a set of bases, is that alpha ij, that becomes 0. And then we have a set of orthogonal bases. This is then the desired property. So let's look at alpha ij and the absolute value of that for n consecutive excitation vectors. And we can look at this for different excitation signals that we have. We can look at this for white noise Wn or for colored noise Cn. And we can say that for white noise, alpha ij is a small number. It's not necessarily identical to 0 because only the expectation of the cross correlation for white noise is 0. And when we look at those short vectors, the inner product is usually not 0, but small. But then compared to colored noise, there the inner product will be definitely larger than what we observe for white noise. Some other signal that we didn't have in the lecture is what is called a perfect sequence, and it's actually a periodic signal. And there, the n consecutive excitation vectors, they're actually perfectly orthogonal, meaning that alpha ij, it actually becomes 0, or a very, very small number, basically our machine precision. And these sequences, like I said, they're periodic and they're created just for the specific task. And just so that you see the difference between this, we will actually use one of those sequences in the Python demo that is coming up. But here, I explain to you the adaptation behavior of the LMS algorithm, not with the graphical geometric explanation, but more with the analytical approach in geometry, using the idea of the excitation vectors needing to span a vector space for a good or fast performance. Let's move on to the Python demo. There we will implement some of the adaptive algorithms, and we will look at the performance for different excitation signals. The demo actually consists of two different files, one script file and one class definition file. And I want to walk you through the script first before I talk to you about the class definition. First, in our script, up there we load the packages that we need, and actually there we also import the class that we have defined ourselves or that we will define. And this class defines the adaptive algorithms. And then the first thing we really do in the script is we load different excitation signals. We load a white noise signal, we load a colored noise signal, and actually for this colored noise signal, I use the inverse prediction error filter coefficients that we used in the previous exercise, and I use these to color the white noise signal that we're using here. And then also we're loading a perfect sequence that I have extended, so that signal contains several periods of that perfect sequence. We also load a impulse response, and that impulse response has 256 coefficients, and we put those coefficients in H. And this impulse response is just an artificial impulse response of more or less white noise. Then we have loaded our signals and our impulse response, and for our simulation we need to create the observed outputs, and we do this simply by convoluting all our loaded input signals with the loaded impulse response. So we do this here separately for white noise, the colored noise, and for the perfect sequence excitation. And then we create our adaptive filters. And like I've already said, we're defining the adaptive filters as classes. So here for each excitation signal that we want to run, we're actually creating a filter object. But what that looks like, we will see later on. Here we're just already looking at how we actually call it. So we're creating those objects with the filter length n. And the one here that I have for the NLMS, this is actually the step size. And then I'm allocating some matrices and vectors because over the adaptation time, I want to save what the estimated impulse response looks like and what my system distance looks like. So here I'm creating several matrices and vectors, and they're a specific length because I will not be extracting that information for every time step, but I will extract this information at every capital N time step. Okay, then here in the next part, we actually do the adaptation, and this for loop is for the extraction of the information. And like I said, we do this every capital N time step. So this is why we have this number up here. And then we do the adaptation for every object that we created. And the filter objects, they have a method called adapt. And that method needs the excitation signal and the observed output. And this method can either work with just one sample, or you can give it a vector of samples. And then we can, in each step, extract our current estimate of the impulse response, because that is a member there. And we can just, because we know our true impulse response, we can compute the system distance and store this in our vectors. And we do this for all our excitation signals, and we do it for all the samples that we have available. And once this adaptation is complete, we can plot the results, and by results I mean the system distance over time, or here the system distance over our iterations for every capital Nth time step. And this we do again for all our excitation signals, so we can then see what the difference is. Okay, this is how actually the script looks like. Now let's go into the adaptive filters class, because there actually the functionality of the filters will be implemented. And this is where you also implement something yourself. Okay, let's start at the top. So we have a overall filter class where we define what is common between all the adaptive filters. And each filter, it has a filter length, so this is n, it has a step size, this is mu, and it has a impulse response vector h, where the estimations are stored, and all the algorithms that we know, they work with a excitation signal vector. So this we also have here. And then we have our initialization function where we initialize all the quantities there. And then I just have a simple method which we will not be using, but you can ask for the length. You can also do a filtering of an input signal with the current estimate, but this is just so that you understand what you can do here with classes, but we will not be using those. What is more important here is the method for our X vector update, because you remember we have the capital N last excitation samples in this vector, and whenever we get a new sample, we need to update that vector, and this function here, this operates on a sample basis. And the actual adaptation, this takes place in the adapt method, and there we can actually work with vectors, and we then iterate with our for loop here over the different samples of our excitation signal and of the observed output. And in this very common adaptation method, we have the basic iterative solution, so that our new estimate equals the old estimate plus our step size times a delta. And this delta function is then defined here as well for this over filter class, but this doesn't actually do anything because this delta is algorithm specific, And this delta we will actually implement then for the different filters. And you can see here for the least mean square algorithm, we derive it from our overall filter class, and then the only thing we define is the delta function. And in this delta function, we say, okay, we need to perform a x update, and then we actually need to prepare a different quantity, and this is actually then the computation of the error, but this you have to do yourself here. And then actually the delta of the LMS algorithm has to be computed from our prepared quantities, and this you should do yourself. The same holds for the NLMS algorithm. So you should know what the difference is between the LMS and the NLMS algorithm. So you can actually compute the error signal and the actual return value there. Then for the Afine projection algorithm, that one's a little bit more complicated. We have some more quantities that we're using. We have, for example, our input signal matrix, and we're also using a output vector here because we need to recompute our error vector. We're using a vector here. And then in our initialization function, we also have our affine projection dimension M. And here I'm also defining our epsilon here because we're using a regularized version of the affine projection here. And then what you have to do here is we always have to update our input signal matrix. And for this, we can actually utilize the input vector update that we have already implemented in our general class definition. So utilize that one. And then you need to make sure that you update the rest of the matrix correctly. And I have prepared this here for you. Whenever you see a question mark, you need to fill in the correct indices or something different. And then when it comes to the computation of the delta, there we're first updating our input matrix. And then we have to update our observed output vector before we then can actually compute our error vector. And then in our update equation, you will see when you look at it that there is a term that we invert. So you first here compute that term that is to be inverted, to then in the last step compute the affine projection delta using the quantities you've prepared before. Now, if you want to fill out the missing pieces yourself, please pause the video as I will now walk you through the implementation. Let's start with the LMS delta update. You see here that we've already updated our x vector and we need to compute the error. And the error is defined as our output sample D minus our estimated output. And the estimated output is the inner product, so NP inner, of our excitation vector and our current impulse response estimate. And when we have computed that error, then the delta that we need to compute is simply the error sample times our excitation vector. And this is the delta for the LMS algorithm. Then for the normalized LMS, this is very similar. Actually, we define the error in the same way. So this is D minus the inner product of our excitation vector and our current estimate. But then the delta is a little bit different. It's our error sample, but here we have to normalize it. And we normalize it by the inner product of the excitation vector with itself. And this then makes a scalar, and this we multiply with our excitation vector. This is the delta for the NLMS algorithm. Then when we go to the affine projection algorithm, there we first have to complete the matrix update function, and we utilize the vector update function by just calling it with the current sample. So it's self.xvec update of x. And then our matrix is basically a matrix that consists of the m last excitation vectors. So we have to shift the last vectors basically to the right and insert the new vector in front. So this is then what we do. The first index we need is we take the entire column, so colon, and we select the columns 1 up to the last one. And there we insert also entire columns. We go from the very first one up to the last one, excluding the last column. And then we can insert into the very first column of that matrix the vector that we've already updated using the xvec update function. And this then completes our matrix update. Okay, so then in our delta function, there we call the matrix update, so we have everything prepared there, but we still need to update our output vector. And here it's basically the same thing we do with our x vector update. So we want to shift all the samples back, the last one drops out, and we insert our new sample in front. So that's why we're using the indices 1 till the end here, and we're inserting there the samples from the first sample up to the last one, excluding the last one, and then the very first element of our vector is then our newest sample of the output signal, which is D. Okay. So how do we then compute the error? And error here is a vector. And we use the output vector that we've just created. So this is then self.d_vec. And we compute the estimate of the output signal by basically a multiplication of our input matrix times our estimate of the impulse filter. So this is specifically a matrix multiplication, so we call a numpy's matmul, and we need to transpose the input matrix, so numpy transpose of self.x_mat, and then of course the second variable of our matrix multiplication is the estimate of our impulse response, and this then gives us the error vector. So how do we get the inverse? First we call a numpy's inverse function, and what do we actually invert? So we invert the multiplication of the input matrix with itself. So we need a transpose there, so we call a numpy's transpose, and we transpose self.xmat, and we perform a matrix multiplication with that input matrix. And here I'm actually using not the matmul function, but I'm using a operator, the add operator, which does the same thing. And this is what we need to invert. But here I'm then also adding our regularization because, like I said earlier, we're using the regularized version of the affine projection algorithm here. And we just need to add our small numbers here on the diagonal of the matrix that we want to invert. Okay, when we have the inverse, we just need to compute the delta. And this is a multiplication of our input matrix times the inverse we just computed times the error vector. So let's write it down. It's self.xmat, matrix multiplication with inverse, matrix multiplication with the error vector. And there you have the delta for the affine projection. Now we can go ahead and run the script. And the first version we're running is with the NLMS algorithm with step size 1. So here's the result. And you have the different excitation signals denoted with the different colors. And you can see, as expected, that our perfect sequence, which has the best properties for a good adaptation speed, converges the fastest. And then the white noise also has a good performance, but then the colored noise, this actually is not a good performance really. You see we converge to very low numbers here. This is because we're not using measurement noise. And basically this is just our machine precision that we are converging here to in our system distance. Okay, now let's change our step size. And I will just do this for the perfect sequence one, so we can actually see a difference, as this step size would affect all the algorithms the same. And you see here now that now the perfect sequence, it actually exhibits very slow adaptation behavior. And of course it doesn't give us any advantage because, again, we're not using measurement noise, but you can really see here that when we reduce the step size, the adaptation speed also becomes slower. Now let me change the step size from 0.1 to the border of our convergence region. And I'm not doing this with 0 because it's very obvious what would happen then, but I'm doing this with 2. And you see here that actually the same thing happens as I would have used 0. We're not adapting at all. You see this here with the green line. We stay at 0 to be system distance all the time. So basically no real adaptation is happening, but we're also not diverging. Now let me change the step size from 2 to 3, and 3 lies outside of our convergence region. And you can very obviously see here in this plot with the green line that instead of converging, we're diverging. This was all I wanted to show you regarding the step size. Now let's change the NLMS algorithm to the affine projection algorithm, and we just need to switch out the name here first. But then, of course, the affine projection algorithm needs the parameter m, the dimension of the affine projection, or the order, and we just need to specify it as 1 here, because I want to show you that then it actually performs the same as the NLMS algorithm. And this you can very clearly see here in this plot. Now let me change the affine projection order for the white noise excitation from 1 to 5. And you can see here that it doesn't really make that much of a difference because the white noise signal was a good excitation signal to begin with. But now let me also change the affine projection order for the colored noise, and there you see that it really makes so much more of a difference, as now the colored noise almost performs as well as the white noise excitation signal. And I used order 5 here because actually our inverse prediction error filter that I used for the coloration of the signal was of order 5. And actually when I change back the order of the affine projection for the white noise to 1, you can see now that they're more or less identical in their performance, because the white noise excitation now works with the NLMS algorithm, but we use order 5 of the affine projection algorithm to remove the coloration more or less from the signal and to make the filter that we excite with the colored noise behave in the same way that it does for the white noise excitation. And this is all I wanted to show to you in this demo. That concludes this exercise video. Thank you for watching.